Hello, beautiful people, and everyone else too. I'm DJ the Deconstructor, and you have entered the Deconstruction Zone. Today we're taking a break from the ultra serious. We're going to look at the difference between science and, well, the other stuff. Today we're looking at Roger Spurr's Mudfossil University, and he's going to be telling us some things about that brand new, exciting James Webb Telescope. And I'm sure he'd never tell us anything silly. Okay, I lied. You'd better stop the video right here. Go grab your favorite adult beverage. You're going to need it.
Okay, my friends, it's just another day in paradise for a Roger. Now I'm looking at the Webb Space Telescope.
Well, hello, Roger. I am so glad you're having a pretty good day. I'm having a good day too. Listen, you said you're going to tell me about that Webb telescope. I cannot wait. I love me some Webb telescope. That thing is amazing. So here we are. I'm sitting back. I'm ready to learn. I want to know more about that Webb telescope.
And they are working in the infrared range, which is a light range that we can't visibly see. We see light at a certain frequency. However, the same particle that creates light that we see is the same particle that creates every other ray.
Oh, Roger, please. It's only been seconds and already you're serving up a steaming hot plate of silly. You're going to make me stop every few seconds, aren't you? So I have to correct everything you say so all this silliness doesn't infect all your listeners. Well, first, light is not a particle. It's a wave, Roger. It is a wave. It's electromagnetic radiation.
It's a wave!
Now, it is true that light has some particle-like properties, but it's still not a particle. It is a wave. A wave, Roger, not a particle.
It's a wave!
Here's the story. Light spins in a circle. And I will show you this, no question whatsoever.
No, Roger. I can show you that light is a wave, and you can prove it for yourself. In fact, anybody listening can do this in their own home, takes no special equipment. What does it take? A couple of polarized lenses from polarized sunglasses. Now, I just happen to have a couple of lenses, and I'm putting them between me and the camera. So you're going to notice what I do here is that I take one lens and I rotate it opposite direction of the other lens. I put them at 90 degrees to each other. When they're at a 90-degree angle to each other, guess what? Light doesn't come through. Here's one in front of the other. Watch what happens when I turn them. The light goes away. It gets dark. Now it's back. It gets dark. Now it's back. Guess what? That's real simple to prove that light is a wave. How does that prove it's a wave? Well, that's because the coating on here is a bunch of molecules aligned the same way to create vertical splits. So when we've got vertical splits on there, anything that can't pass through the splits bounces off. Now I've got a second pair. I align the splits the same way. Guess what? Light passes through. I turn one so the splits are the other direction, and now light is blocked because what was going this way has to try to go through this path, and it can't. It gets blocked. These are polarized sunglasses. For a couple of bucks, you can prove it yourself. If light was a particle, a circular spinning particle, it would either not pass through the first lens, or if it passed through the first lens, it would also pass through the second. It doesn't work your way, Roger. We know what light is. It's been proven. It is not a particle. It is a wave. Can we please get back to the James Webb Telescope? I would love to learn something about the telescope that I don't know. Please, Roger, let's get back to the telescope.
And not only that, it is a particle, and I will show you that, no question whatsoever.
Roger, I'm going to ask you to do something really, really difficult. I'd like you to think about what you're saying. Think about what would happen if light was particles. I have in my hands an old-fashioned light bulb. Now, particles have mass, waves do not have mass. When the filament heats up, it gives off thermal radiation. We see that as light. So that means particles would have to be coming out. Where are the particles coming from? They would have to be coming from the filament. But guess what, Roger? You can take this bulb, weigh it before you turn on the electricity, weigh it after. It weighs the same. The mass doesn't change because no particles are leaving the filament. Light is a wave. It's a wave, Roger. It's a wave, not a particle.
Too much light! Too much light!
So as it spins, it impacts what's in front of it. Now, if it's spinning slowly like this, you know, around and around and around, but very slowly, it's a red wave. If it's spinning like this, when it impacts, it's a blue wave. Well, what is the blue different from the red? Blue means it bounces back harder. That's all. This is coming this way, it's going bump, bounces back. This is going pow.
Oh, that's not right. No.
Roger, there's almost too many mistakes in that to even talk about. First, light is not spinning. We already said that, but it's not a particle, so when it hits something, it doesn't hit anything harder. We have formulas for this. We understand that the speed of light is equal to the frequency times the wavelength. I've got a formula here. I'll show it to you. But what this really means is the amount of energy in there has to all balance such that if we increase the frequency, the wavelength has to change. If we change the wavelength, the frequency has to change. But what doesn't change is the speed of light. That is a universal constant. Light always travels at 3 times 10 to the 8th meters per second. It does not change, Roger. It does not change. Now, as far as bouncing back is blue. I mean, wait a minute. Don't you understand that the only light we see is the light that comes into our eyes? And our eyes are not being bombarded with particles. We are detecting color based on wavelength. The longer the wavelength, the more red the color. At the other end of the spectrum that we see the violet, which is a very short wavelength. And it doesn't have anything to do with light bouncing back. Please, can we get back to the Webb telescope?
All it depends on is the orbitals around the nucleus of what it hits. Well, what is the orbitals? Well, you have a nucleus of every atom. Every molecule has atoms, and the atoms have a nucleus, which is the core of the atom, and then it has a cloud of electrons. If they're way out here, and it gets bumped, you get pretty much red because there's just a cloud. It goes poof, poof, and bounces back. If it's way down here, very tight to the nucleus and it hits, it goes boing, and just shoots back like a bazillion-ton spring. Okay, way out here, it's just way out here, and it goes boing and pops back. But if it's way down here, it goes bing, because this one here is held tighter than hell.
Roger, what you're trying to describe is luminescence and fluorescence. We're not talking about light bouncing back in the cases where it strikes an electron. What we're talking about is that when that wave hits an electron, it imparts energy to that electron. The electron changes from what we call a ground state to a higher energy state. That actually slightly changes its orbital position. Now, think of it this way. It's like an elevator car going up. Light hits that. It takes energy to raise that car up. That car is the electron. But the car can't stay up there for long. It has to come back down. When the car comes back down, a new wave is emitted. The old wave was absorbed. The new wave is when it falls back from its elevated state, its excited state, down to the ground state again. And when it does that, you get a specific frequency of light, a specific wavelength that is unique to that atom. It has nothing to do with the electron being further away from the nucleus or closer to the nucleus. I'm beginning to think that you don't even really understand what an electron is. I hope you're not going to tell me something silly about electrons.
When you break them off of the real close ones, you get some power. That's why hydrogen is so explosive. It's all it is made of electrons. It's made out of these two particles, just like that, in a mass of about 1836 or so of them in a ball.
Oh, that's not right. No.
And then one more of these same particles, a dipole, black and a white, wants to get in. The white wants to get into the dark core of the center. And it says, no, you cannot get in. All right, you can stay right out there. That's as far as you can get. And there's 1836 of them here, or 1835. And it wants one more to become 1836 neutral. Well, it can't get in there. Because all the white ones surrounding that black core say, no, well, there's enough white ones. You stay out there. You can stay right there.
Why are you doing this?
Why are you doing this?
No, Roger. No. No, no, no. Hydrogen is not composed of only electrons. Atoms have three primary particles. They have electrons, protons, and neutrons. That's it. Now, yes, protons and neutrons are composed of quarks, but an electron is the largest quark and it cannot be subdivided into anything else. That electron is not part of the nucleus. It is outside of it. And when you're talking about hydrogen, hydrogen usually only has a proton and an electron. That neutron is nowhere to be found because the function of a neutron is to help hold protons together, because protons have a positive charge, electrons have a negative charge, and that's all there is, Roger. You do not have 1836 or whatever you said it is for a proton or for the nucleus of an atom. You have protons, you have neutrons, and this is fundamental to even the way we've arranged the periodic table. So stop, Roger. Let's get back to the Webb telescope. Maybe you can tell me something new and interesting about the telescope.
Now, if you inject a spark in here and you interrupt this stability, everything blows. All the particles go at the same time, and the explosion is just horrendous from hydrogen.
Roger, no. Please stop. I wanted to hear about the Webb telescope, and now you're still doing this. Okay. Hydrogen atoms have one electron and one proton. Maybe they have a neutron, but most of the time, no, they do not. So it's a proton and an electron. And you're saying, introduce a spark in there and it goes boom. Do you know what a spark is, Roger? It's a bunch of electrons. How do you get a spark down in there? You're not getting a spark down in there, Roger. And putting other electrons around it is not going to have any effect whatsoever. Because guess what? I can take a tube filled with just hydrogen gas, and I can have a positive cathode on one end and a negative anode on the other. I can run a stream of electricity through there. I get no boom. I'm going to show you this. I get no boom. What I do get is I get light. I get light of a specific wavelength. No boom, Roger. And what's happening? I'm pushing electrons through there. Electrons plus hydrogen do not make boom.
And the particles we're going to be looking at are those little black and white ones right there. and you see their orientation, they spin this way. They don't tumble like this. This has really got me freaked out because I can't understand how it's possible. Each one of these is a wave.
Roger, what is it you're showing me on that screen? It looks like you took a cell phone image and you blew it up, and now you're seeing pixelation. You're seeing artifacts from an image that you stored onto your computer. If you store an image on a computer and you zoom in and you blow it up and keep blowing it up, all you're going to see is the pixelation pattern that makes up the image. You're not seeing electrons, Roger. You cannot see electrons with a cell phone. And let me ask you this. If you really thought you could see that with a cell phone, I'm going to give you a challenge. Every living thing is made of cells, and you can go out on the internet and you can see pictures of cells. If you can take a cell phone and zoom in with a cell phone to see atoms and to see electrons, then you ought to be able to stop before you get to that level and see cells. If you can see cells with a cell phone, I will apologize to you and retract most of what I've been saying, but light is still a wave. But Roger, you can't do it. The reason you can't do it is because you cannot zoom in with a cell phone to that level. Not at all. End of story. Can we please stop this nonsense and get back to the Webb telescope? You're wearing me down, Roger. I don't know how much more of the silly I can take.
All right, I've been talking about push to shove, and this is what you see here.
Oh, that's not right. No.
As this spins in this direction, you see it tightening this way? It's crushing its field into the center, and the arms that stick out they consist of particles.
Oh, that's not right. No.
And they're crushing into oncoming particles that are surrounding the world or the universe. So what happens is they bend backwards, plus they concuss, causing push to shove glow.
OMG, Roger. I would be LOL, but this really isn't funny anymore. What you're looking at is an artist's representation of a galaxy. And down in the center, this is not fields crushing down. There's probably a black hole there, and that black hole is a gravity source, and that gravity is keeping stars and planets in that region. It is not fields crushing down. This is not the way anything works. And those streams coming out there, the arms of the galaxy, those are not particles, Rogers. The bright, glowy things are stars, Roger. You do know what a star is, don't you? It's like our sun, only a lot of them are a lot bigger. It's stars. It is stars. It's a galaxy. And it is not a bunch of particles around our world or the universe. You do realize the universe is filled with trillions of galaxies, like what you're looking at there, and not all of them are spiral galaxies. They come in a lot of different shapes. So no, Roger, it's not a spiral, it's not crushing down. In fact, let me show you what happens when you have mass and a spinning object. Stuff does not crush when it spins, it goes out the other direction. And why are those arms curved? It's simply because they're moving at a slower rate around this central gravity source. That's it. It has nothing to do with forces crushing down. And once again, these are not particles, Roger. They're stars. They're stars.
These are repulsion patterns. These push this way, and these guys try to push back, and they say, no, you can't push me, you can't push me. And they create this zone here. It's called the Casimir effect.
OMG, Roger, come on. This push to shove stuff? No, the blank areas there are areas where there are no stars. That's why they're blank. And it's not because forces are repelling each other. It's just a region with not a lot of stars and not a lot of things in it. It's just an empty area of space. And it's also not the cashmere effect. Cashmere is wool. It's a sweater, Roger. I think what you're trying to say is the Casimir effect, but the Casimir effect is not push to shove, blah, blah, blah. The Casimir effect has to do with quantum fluctuations impacting things on the microscopic level. So it's movement on the microscopic level that you're going to see or notice because of quantum fluctuations. Now that has nothing to do with galaxies and gaps between bands of stars in the galaxies. The Casimir effect is once again quantum fluctuations noticed on the microscopic level. Can you please tell me something that makes at least a little bit of sense?
Sound is nothing more than the same exact particle. It's just not fast enough to turn into light.
Oh, that's not right. No.
Roger, sound is not a particle. And sound does not become light because it gains more energy and moves faster. Sound is a disturbance in a medium, such as air. Sound actually travels through water. You can have sound waves through water. They're usually called sonar, Roger, and it's not a bunch of particles. It's easy to prove because you and I both know particles have mass. If I step on the scales and no matter how much I scream, I can't lose mass. I could scream. I have stepped on the scales and screamed, and I still weighed way too much. So no, sound is not particles. Sound is sound. It's not an electromagnetic wave. Light is an electromagnetic wave. You cannot change sound into light, Roger. It does not work. In fact, I've had it. I'm done. I don't think I can take any more silly.
No, this has to stop now.
By the way, this is Sunshine. Sunshine wants you to like and subscribe and turn on the notification bell so you can access new content as it's released. If you don't like, subscribe, and hit the notification bell, Sunshine will know, and she'll come to your house and she will deconstruct something. Until next time, this is DJ the Deconstructor wishing you happy sciencing.